about few instructions which has been already although posted on the WhatsApp group, but still I just want to revise all of you. A minimum attendance of 80% across all the session is compulsory. A minimum score of 70% in the assessment is mandatory. And this is important. And the submission of compulsory online feedback of the attendant FDP through the Atal portal is essential requirement for certificate generation. So for this, till 20th, we'll complete all the process from our end, like submission of the assessment marks and the attendance. And then only you people can upload this feedback. Okay, so just be active for few days on this WhatsApp group so that we can give the updation about it. So yes, and submission of next is submission of reflection journal is an essential requirement. Okay, already. Okay, fine. Okay. So if you have any doubt, so you can consult us later on.
Session 11. That one is session 11.
So now, before we begin to the technical session 1, I would like to take a few moments to introduce our resource person. So we are pleased to have with us our first resource person for today, Mr. E. Mondal, currently serving as Divisional Engineer at WBSEDCL. A warm welcome you to, sir. Mr. Mondal has over 13 years of professional experience in the power distribution sector with extensive involvement in project execution, customer services, revenue management, substation planning and design, and distribution operations. He has served in various capacities, including station manager, divisional engineer, divisional manager, and currently divisional engineer at WSEDCL. He has successfully implemented national distribution programs such as IPDS, RDSS, NDDUGJY, contributed to loss reductions, and executed multiple substations commissioning and system strengthening projects. He has also undertaken specialized technical training at institutions including CPRI, IIT Kharagpur, and GSES, and has working proficiency in MATLAB, ETEP, SQL, and SAP. We are delighted to have him with us today. So with this, I would like to request Mondal sir to please take over the session. Thank you.
Yeah, thank you so much. So my introduction has already been given. So I'm not going to again introduce myself, but I will say something. Firstly, good afternoon, everyone, all the participants here. And I am, as introduced myself, I am Endadul Mondal, and I have been serving as Divisional Engineer Electrical in WBSEDCL for the past 13 years. Firstly, I would like to thank all the faculty members of NIT Durgapur for giving me such an opportunity. And I am really glad to be here to share my thoughts, and as well as from learning all of you from all expertise here present today. And my presentation today is on the modernization of distribution networks. So I'll go to the, I'm just presenting my slide. Please let me know whether is it visible or not. So is my screen visible?
Yes, sir, it's visible.
Okay, thank you. Thank you. So let's start with the presentation. So my today's topic is modernization of distribution networks. In this session, we will talk about the new challenges and opportunities in power sector, especially related to renewable energy, smart grid technologies, and improving the reliability of distribution network. So I look forward to an engaging and insightful session today with you all. So all of you know that more than 70%, 73% of the greenhouse, global greenhouse gases is emission. That is emission by the energy sector. And because of this, you know, all of you know that mostly earlier we are dependent on the coal-based generation. So, and because of this extreme greenhouse gas emission, so we have all the major countries have an agreement, that is Paris Agreement, where we have actually set a goal that we should not increase the temperature further 1.5 degrees centigrade. This is an average, not but the thing is that during the Paris Agreement, it has not been specifically not mentioned that whether what is the actual is from where this 1.5 degrees centigrade will be enhancement of the temperature will be considered. And this because of this
सर वो आपकी स्क्रीन दिख नहीं रही है सर प्रेजेंटेशन.
No,
Okay.
it's visible. I think there is some
Yes.
connection issue. Yeah, it's
Yes, sir, it's visible.
Okay.
visible.
So please check your internet. Okay.
Okay, sir.
So the energy sector is the single largest contributor to the climate change, and according to the International Energy Agency, this data is 73% of the global greenhouse gas emission by the energy sector. But renewable are because of this we have government all over the world, the government or all the all the countries has taken an initiative for switching from the conventional coal-based or gas-based energy to renewable energy. So if you talk about the in India, so that is throughout the globally, around 33% of global electricity generation has been jumped from 10% in which was 10% in 2010. And sorry. And if you talked about in India, so that is in by 2030, current scenario that 190 gigawatt solar has already been installed, and we have a target by 2030 we will install 500 gigawatt of non-fossil fuel capacity by 2030. So this is the as on 31st March 2025. It was the scenario. Total installed capacity was 475 megawatt. Out of which the major contributor was coal-based generation. Coal, and you can talk about if you take the coal and oil and gas, this contribute more than 52%. And solar, whereas solar and that is solar and wind, that is contributing around 33%. So this is the data based on the 31st March of 2025. And if you and if you see this here, actually, that is the capacity addition in 2000 from March 2019 to March 2025. We can see that no other, capacity addition in coal, that is black in color, that is slightly increased, not much, in comparison to total. If you take the total, so you can say negligible capacity addition has been in the coal-based power plant. But if you see this green, I mean, that is renewable energy. So major the capacity addition has been taken place in the renewable energy sector. And this is our trajectory for 2030. We have a we have a target of installing 800 gigawatt of total capacity to meet up the future demand. And this is the total 2030 projected capacity, but out of which this is our target. So we have to we have a target of 280 gigawatt of solar installation, and we also have a target to enhance wind to some extent. So in that case, if we talked about, if we think of 2030, then we can see that is actually solar and wind that is contributing 50%, and coal-based power plant is contributing only 33%. Now, but what is the impact on the grid? That what happened in earlier when we have actually only coal-based generation was there. So that time we have only we are actually known that how much generation in my hand and how much generation we can actually give into the grid. And not only that, our prediction that power only flow in the only unidirectional. It was the convention, and we have the advanced forecasting and auto. But we know that how much generation we'll get. But when the renewable energy integration taken place, so that time, two major challenges is here. One is that actually power will flow the bidirectional. Second is that the forecasting. It is not known earlier when the coal-based generation was there. It was known to the engineers that how much generation I will get based on this, I mean, coal reserve, or based on the, maintenance, all this, including all. It was actually known that how much generation I can get. But due to integration of the renewable, it is quite natural that I will not predict that how much generation I will get. But because it is variable and intermittent kind. So what is actually needed? So two-way power flow capability, the grid should have the two-way power flow capability. The solar rooftop and relevant system can send power back to the grid. The distribution network must now handle the electricity going in both directions safely. And advanced forecasting and automation. Renewables are very actually weather dependent. So we need better forecasting tools and automated system to balance demand and supply in real time. And energy storage integration. So energy storage system like batteries help smooth out the variation in solar and wind generation. They improve the reliability and reduce stress on the grid. And updated regulatory reliability strand. This is actually earlier what has happened. I will later. I also have a slide. What happened that regulation was not much strict for the renewable energy resources earlier, but because of the huge integration of the renewable energy resources from multiple players, so we have to think about the stability of the whole power grid. So because of that, some regulatory imposes is there, both for the generation and as well as for the for stabilizing of the grid. They have the imposition. If you install, suppose if you install a 200 megawatt of solar plant, so you have to keep at least 50 megawatt of battery storage for continuous 4-hour power supply. So this kind of imposition from regulatory body is now it is coming. And reliability standard, all actually what we are doing and what the grid, what we are taking the projects for modernizing the grid, that actually will be assessed by these reliability indices. So this is the key challenges. Key challenges, all of you know that whether all the renewable energy resources, that is wind and solar, that is intermittency and variability. We don't have the prediction that how much generation we will get from there. It is actually variable in nature. And it already I mentioned that this generation is actually weather dependent and require balancing through storage of flexible or through flexible generation. And energy storage limitation, we know that whatever the technology is available currently, though the some apart from that thermal and hydrogen storage, though it is still not been in a large scale, it has not been still implemented. But what we say in energy storage limitation in terms of, if we talk about the battery energy storage system, so though they doesn't have the a large scale capacity to actually they have the limitation that we can't do that beyond a certain capacity, it will be uneconomical. Because overall we have to think about the economical. So beyond a certain capacity it will not, and not only that, it will not if you such situation occur, then like if you have a Duncan flat like a situation, so that time the battery energy storage system is not thus it will not be able to actually supply the energy for the throughout the for rest of the 5 days or 10 days. So grid integration issue. Existing grids were designed for the centralized generation. Integration of decentralized renewable demands grid upgradations. Because suppose grid integration issue, firstly, that issue is that suppose someone is planning to install a solar capacity that will be connected to grid. But the thing is that where the plant is being set up, they are actually have some actually transition, constant in transmission of power. Or not only that, they may have some constant in the power, power transformer too. Suppose you have installed a capacity of 400, suppose 100 megawatt of capacity, but you are where actually it is coming to the, but actually it will be routed through a transmission line and it will be routed through some power transformer. So if we see that some power transformer is in actually due to the installation of this plant, that some power transformer is coming into the overload condition, or some transmission line is going beyond their thermal limits, or so that time this kind of integration issues is there apart from the stability issue. Reduced system, system inertia and stability issue. So all of you know the conventional, actually whenever we are actually demanded, depending on the coal-based generation, that time the rotating inertia that is in the was actually one kind of giving physical inertia into the system. But because of this lot of integration of renewable energy resources, and due to this integration in the daytime, mainly in the daytime, we are not getting that much of inertia which is required for actually stabilizing the system. I already mentioned the transmission constant and policy and regulatory barriers. That is inconsistent policies and slow permitting process. Suppose someone is actually trying to implement, or some player is coming to the that would like to install a solar plant or wind power plant. So there always have some issues of regarding policy, regulatory barriers and policies. may not be allowed due to the may have some constraint on forest, or may some constraint of you can say land. So government should have a policies, or we should have a make some regulation that will help to implement this renewable energy resources. Land and environmental impact, large land requirement. In all of we know the for solar power plant, you can say approximately we can say that for 1 megawatt of solar we can require more than actually one acre of land. So that is huge. At least approximately if we talk about. Then actually huge land required, not only for the even for wind also, because we need whenever the wind where the wind power plant is being installed, so there actually free land is required for flowing the air. So large land requirement for solar and wind farms, and potential conflicts with agriculture and forestry and biodiversity. Economic viability and market design, need for dynamic pricing, carbon markets, and fair grid access. Intermittency and variability. Unlike conventional power plants that provide stable and controlled output, renewable energy resources such as solar and wind are inherently weather dependent. Solar generation drops during cloudy condition or at night, while the speed fluctuate, and while the wind speed fluctuate unpredictably. This variability actually leads to the generation demand imbalance. All of you actually heard about the dark curve, which is actually key concept in modern power system operation. So during midday, solar PV generation is at its peak. This significantly reduces the demand that the grid must supply from the conventional resources like coal, gas, or hydro. In the evening, solar generation rapidly falls as the sun sets, while electricity demand sharply increases. From the evening, electric demand increases, whereas the solar actually generation is actually tends to zero. So the net demand rises steeply. So it actually because of this actually dark curve, we actually what is actually needed when in the one hand we are not getting the generation from the solar, so we have to switch on the conventional resources, either hydro or coal based, or sometimes you can say actually gas based plant or fast acting plant. So during this evening time, what happened? We have to ram up the our generation. So what is the then that per hour we may require 100 megawatt of power. So in that ratio, we have to set this RAM rate so that sometimes it may become actually what can I say, may create instability, that it's required so much of RAM rate that it is not quite impossible to raise some to increase the generation at a rate. And voltage and frequency stability, that as the I already told, as the wind and solar, that is actually all the times it's fluctuating. So there may have some, if you don't have quite measures, if you don't have sufficient grid strength, if you don't have the sufficient grid strength, so that time you will face this voltage fluctuation and frequency variation also. So during the Duncan-Flatter events, the core challenges is that extend period. What is Duncan-Flatter? That is Duncan-Flatter. During this Duncan-Flatter period, that is actually we are not getting actually sun rays, and as well as the wind is not blowing. So this is the in this condition when there is no sun rays and there is also not wind is not blowing. So in this phenomena, what will happen? The generation, generation from solar and also from the wind will not get generation. Less generation, you can say. So this event is called generally Duncan flood. So if it stayed more than 2-3 days, so what will happen? Because we already said that conventional batteries will not be able to supply your actually energy for the long days. Battery energy system may have give you some support for stabilizing your grid, but it will not. It is not for the intents that it will supply you power for a long stage. Though, so because of that, what we can do, we can have some long duration energy storage. So we can have pumped hydro storage, mature technology for large scale and daily and weekly energy shifting. Green hydro and hydrogen are others, though the efficiency of hydrogen batteries, that is not actually less than, at least it is around 35 or 40%, not more than that. Though some research work is going on so that the efficiency can be enhanced for the hydrogen based batteries. And so this is the schematic diagram. All of you know actually aware of this fact that in the daytime pump hydro storage, what we do in the daytime when there is excess solar energy is there, so we utilize this energy, and from the lower reservoir we push the water to upper reservoir, and during the when it's energy required or in the evening time, we actually just utilize this this store store water to run this generator, so that we can meet up the demand at the evening time. And not only that, it's what is happening in the daytime. If you see the price of the energy, so that time in the daytime the price of the energy is quite low, but at the evening time price of the energy is quite high. So this, if some utility have some hydro storage, so it will be make the utility beneficial. There are different kind of energy storage system is available. That is electrochemical storage. So lithium ion batteries is there, flow batteries there, sodium ion batteries there, solid state batteries there. Chemical storage, palm hydro storage is there. I already talked about. Compressed air energy storage is there. Flywheels may have some flywheels. Thermal storage, that is molten salt storage is there. Electrical storage, hydrogen storage, or super capacitor is there. But the limitation of the I already amongst to the limitation. That battery energy storage system have high initial capital and replacement cost. Most storage technology can supply energy only for a few hours, around 4 hours. If we whenever we actually in WBCTCL, we also have some we are actually planning to have to install a battery energy storage system of 100 megawatt for 4 hour for meeting up supply of energy for 4 hours only. And large scale energy storage actually still in developing stage, and round trip efficiency typically 70 to 90% for the apart from hydrogen battery. Research into advanced chemistries is still in process. To reduce system inertia and stability issue, conventional generator provide mechanical inertia that stabilize frequency. Renewable system like solar PV and wind with inverter lack natural inertia. So rapid loss of inertia leads to frequency deviation and voltage instability. What is the mitigation? Mitigation techniques are there: synthetic or virtual inertia using inverter-based resources, fast frequency response through energy storage, advanced control algorithm for inverter dynamics, grid forming inverter and hybrid system, renewable plus synchronous condenser, enhanced real-time monitoring and protection schemes. So a sharp decline in rotation energy. So if we talked about the rotation energy 2010 in the daytime, so that was, it's a rough figure, it's not exact. That is the rotation energy that was 450 gigajoule, and now in 2024 it's around 280 gigajoule. So all of you know that rate of change of frequency that is dependent on this actually. Rate of change of this frequency actually dependent on this rotational energy, because this rotation energy actually determine the system inertia, that is H, we generally call this H, and rate of change of frequency inversely proportional. All of you know that inversely proportional to H. So if you actually rotational energy, as the rotational energy, storage rotation energy is being reduced, so rate of change of frequency is being increased. So there's small inertia reduction and frequency stability in modern power system. So if you see this graph, so you can see that is when there is a high inertia, that is, this is the blue line. This actually there is no and low inertia. If you see this graph in red, so we can see that this frequency actually falling not sharply, frequency is falling steadily at around here you can see, if you if you talk about this 4 seconds, in 4 seconds this much of frequency was there, but for when the low inertia scenario, so that this much of frequency is there, then what is happened, we all of you know that there is under frequency relay is there in every power generation. So what will, in due to this sudden fall of this frequency, because if you don't have get time, if you, what is required actually, suppose some fast acting generation or switch on of the battery energy storage system or auto, if you it's also automated, then also it required millisecond range of time to actually release the power. So this much of actually time the system required. So because of that, if you suddenly actually rate of change of frequency change, actually if the frequency change suddenly, so what will happen, that the system will not get enough time to react. So in the low inertia case, this is the graph, and adding fast frequency response, so that time the curve slightly improve. And adding inertia, if you add inertia, then also this curve slightly improve. Actually, it's trying to copy to this actually high inertia graph. And low, if the low inertia, very steep frequency drop, high inertia, lower and safer decline. Added inertia that reduce ROCF, raises frequency, nothing, buys time. Here actually buys time for the controllers. Inertia determine how fast, inertia determine how fast frequency falls, not where it finally settles. If you, am I audible? Have you any? Do you have any question? If you have any question, please write it down. I mean, at the end of this session, please ask, because time is limited.
Sir, what is Nadir requirement?
Sorry.
Nadir
requirement means actually Nadir requirement. There is a preset. I mean, whenever if you in the power plant, whenever you have the generation, so you have the under frequency delay, right? So that time you have to set the at what frequency you would like to actually trip the system.
Yes, sir.
So that the minimum range. I mean, this is the range of this frequency. That below of that will not. The system will be at risk.
Sir, actually, frequency tolerance is like plus or minus 0.5%.
Frequency tolerance is there, plus minus 3% is there. What are we talking about? Plus minus 5%.
No. Plus minus 0.5%. Like
No.
50%.
Actually, frequency tolerance is there, plus minus 3% is tolerance is there. But the thing is that,
Yes,
beyond that, if it's go beyond that tolerance, then you have a frequency deviation. Here it may not be exactly. I have not drawn this curve exactly right there, but the nadir is there. The system should not go beyond that. Suppose I have designed a system, or I have put a solar power plant so that it will actually rate of change of frequency will in such a manner that will cross that nadir frequency before responding other actually frequency, other what can I say, that is other primary or other primary control, or other, if you have any fast acting generation plan. So you should have that much of time. Suppose this actually drop, you can say 4 seconds, but you can say roughly 4 seconds, okay, or 5 seconds, but your system needs 6 seconds. Suppose your system control, your primary control needs 6 seconds to respond, though it take much less than that, but you need. But if you talk about the governor response, so it will take around 3 seconds, around 2 to 3 seconds. So within these 2 to 3 seconds, because it should not go beyond that limit. Am I clear?
Okay, sir. Okay, sir. Thank you.
Okay. Frequency control, all of you know this. In book, you already you actually much more familiar with this such kind of curve. So during firstly, when the rate of change of frequency initially due to the system inertia, that is rate of frequency. What will be the rate of change of frequency that is being determined by the system inertia? System inertia as well as the frequency, because if you see the equation, then you will see that that is 1 by 2h f0, then something other terms, and that is mainly determined by the system inertia. If you talk, then what the function of the system inertia to actually buy the time to response for the primary control. So reduce system inertia and stability issue mitigation technique. But synthetic inertia or fast response frequency, fast frequency response, energy storage system, synchronous condenser rotating stabilizer, grid forming inverter, fast acting generation plant, gas turbine and hydro units for primary reserve and RAM of support, and advanced control and protection. So these are so if you have the low inertia, what will happen? The inverter based resources, solar, PV, wind, no rotating mass, high rate of change of frequency. As we seen in this graph, in low inertia condition, it is high rate of change of frequency. Grid faults and generator trips. So if you have a high rate of change of frequency, then your generator may be actually tripped due to under frequency delay. So what are we have the techniques? We can add synthetic inertia, grid forming inverter, and fast acting plants. If you have some hydro plants in your hand or gas power plant in your hand, so that you can quickly boost or quickly actually quickly enhance the output of this generator. Short-term stability changes, fast responding, we dispatch open cycle gas turbines, and we already talked about this. Now, why the grid modernization become essential? So renewable energy, 1 minute. So renewable energy rapid growth, renewables are now supply 30% of global electricity. And 500 gigawatt on non-fossil. And in India, we have already told 500 gigawatt non-fossil fuel capacity by 2030, bringing massive solar and wind integration. And addressing core renewable challenges, intermittent and Duncan-Flatter-like situation, reduce system inertia, transmission congestion, system strength, changing aging infrastructure, rising demand. And not only that, even also we are not aware about the data center. Nowadays, because of this data center, actually we are not able to predict the how much energy, how much demand will come. Because currently data center, it was not in the concept. So nowadays, because of this AI and all this, IT based, so data center is now actually big challenges. And because of that, we are not able to predict that how much energy growth will be, how much demand growth will be there in future. And non-negotiable reliability and power quality, digital economics need near zero downtime. Side less are essential. Mandatory outage, momentary outage, MIFI, and voltage dips can disturb industry and data center. Grid management is the backbone of the stability as sustainable energy future, ensuring resilience, reliability, and readiness for the decarbonization of the world. So this is the definition of the grid. Definition of grid modernization. Grid modernization refers to the process of upgrading the existing traditional electric power grid with advanced technologies, mass infrastructure, and innovative practice to make it more resilient, reliable, secure, affordable, flexible, sustainable, and capable of integrating renewable energy and emerging resources. It ensures the grid can meet the future energy demands while addressing challenges of efficiency, safety, and environmental responsibility. So the what actually just some attribute, the resilience, the ability of the withstand, anticipate, recover rapidly from the high impact events. And reliability, a consistent supply of electricity with minimum interruption, ensuring compliance with safety standard, meeting SAIDI targets. Flexibility and adaptability, the capability to handle highly dynamic two-way power flows and efficiently integrate renewable energy and electric vehicles. Security, enhanced protection against physical and cyber threats, especially to supervisory control and data acquisition system. Because whenever you have the modern grid, so that time you are, if you have implemented SCADA, so all the system is automated. So what is happen? If you have any cyber threat, so you may have face malfunction. Suppose you are trying to switch on a breaker, so that time you may have that you are trying to switch on, but it is getting, it is not off, or it is switching on another breaker or switching off another breaker. So clean and affordable, maximizing the integration of renewable energy and ensuring power system economically. How to modernize the grid? Digitalization of the grid, install smart meter, sensor, communication system for real-time monitoring and control, use AI, big data, and predictive analytics for fault detection, maintenance, planning, and demand forecasting. Automation and smart control, deploy automated switches, reclosures, self-healing networks for quick fault isolation and restoration. Implement SCADA and advanced distribution management system to enhance visibility, reliability, and coordination. Integration of renewable energy, connect solar, wind, and hybrid system using smart inverter and flexible interfaces. Integrate energy storage system, batteries, pump hydro, hydrogen to balance variable generation. Virtual energy, use power electronics and control algorithm inverter to emulate the stabilizing effect of traditional rotating machine, maintaining frequency stability in renewable rich grids. And decentralized and flexibility, distributed energy resources like rooftop solar, EV, and microgrids, deploy virtual power plants. And another concept is that is virtual transmission lines. So you can also, suppose if you have the actually congestion in your transmission line, so that time what you can do, you can bring this concept of virtual transmission line. Advanced power flow control and storage system, virtually expand transfer capacity without building new lines. So as we have the time constraint, and just skipping some slide, please don't mind. So what is the power system reliability? So power system is the measures of the electrical system ability to supply continuous electric power to all customer at an acceptable level of the quality and in the required quantity. It is essentially the probability of a normal operation of the electrical grid at a given time. IEEE 1366 of 2012 provides a common language and a rigorous statistical framework for quantifying the reliability of an electrical power distribution system. So these are the indices that is being defined in IEEE 1366 of 2012, though it has been amended later. So that is indices. All of you heard about this SIFI, the system average SIFI, system average interaction frequency index. What is actually quantified? How often an average customer experience an interaction. KID, customer average interaction duration index, average time to restore an interaction. Suppose one interaction happen, but how much time it will take by the utility to restore that power. SID, system average interaction duration index. This is actually SIFI and this is SID. This is actually frequency. Then how frequently power is getting off, and this is SID, how long the power, if the power is interrupted, then how long it will stay. That is actually SID. System average interaction duration index. So how much hour you will not get power. Suppose one power is gone, how much hour average, on an average, how much hour you will not get the power, or how much minute or how much second. MIFI, momentary average interaction frequency index. Now it has been bringing an actually new because MIFI, this is one kind of, you can say SIFI, but MIFI is different terms. So which actually, suppose power is gone and again power is came within 5 seconds. So the interruption which are actually stay less than 5 minutes, that is actually bring to another category, that is MIFI. And KEMI, customer experience multiple interruption. In some areas you may suffer that some of the consumer is getting multiple interruption. Suppose you have later on we are coming one by one. So defines method, IEEE standard 1366 of amended in 2021. So defines SID should be less than 115 per year. SIFI should be less than 1.5 year, 1.5 per year. SIP, that is another index, average system interaction frequency index, and average system interaction duration index. So this is actually, in this case, if we, this is actually this frequency interaction weighted by the amount of load affected, and the total impact of outage duration weighted by the load affected. So if you talked about the SID, this is a small example of the SID. So suppose a system has this is the total average duration of interaction. This is the universal actually formula, you can say. Suppose a system has 1,000 customers, outage 1, 2 hours affecting 500 customers, and outage 2, 1 hour affecting 300 customers. So what is the summation of this divided by NT, total number of customers served. So total number of customers here 1,000, and outage duration at location I, and number of customer affected. So this is outage duration. Outage duration what? 2 hours. So affected consumer 500. So 2 into 500, that is plus summation 1 into 300 customer, that is 1.3 hour per customer. So SID, in this case, SID will 1.3 hours per customer. That means if for a customer on that locality, for a customer, if the power goes off, so that will not come on an average 1.3 hours. He will not get power on an average 1.3 hours per year. So utilities use SID to identify weak spot in the grid. A lower SID indicates better reliability. Regulatory agencies often set benchmark SID less than 2 hours. Then SIFI, it was the duration, it was the frequency. So suppose a system has 102 hours affecting, so how much customer it has here affected? 500 plus 300, 800 divided by 1000, that is 0.8 per customer per year. That means if you 0.8 but not less than one consumer in a year, it is being affected. When less than one consumer, you can say less than one consumer experiencing power off in a year. KID, customer average interaction duration index, measure average time to restore service once an outage occurs. It answers when the light go out, how long do they stay out? So that is actually, if you take, that is summation of customer interaction duration, they have a total number of customer interaction. That is here actually in the denominator, here actually coming total consumer, here it will come how much consumer affected. So 2 into 500 plus 1 into 300 divided by 800, 1.625 hours per customer. My fee, the momentary average interaction frequency index, it's just like of psi fee, but it is here actually which the interaction which will stay less than 5 minutes. So that is being actually coming to these indices, my fee momentary average interaction duration index. KME, customer experience of multiple interaction. So these are the actually, you can say, distribution reliability indices, all whatever, but some generation in reliability indices are also there. So these are actually lowly, loss of load expectation. So lowly, there is actually expected duration when the generation is insufficient to meet the load. How long storage, and second index is that a LOL. So loss of load probability that the available generation less than demand at a given time. And another that is ends expected energy not served, expected unserved energy due to capacity shortfall. And for force outage rate, probability that a generating unit is unable when required. Now, loss of load expectation. Loss of load during is expected duration in days or hours per year when the available generation is not enough to meet the demand. So it measures how long the system is expected to experience a shortage of generation capacity over a given time period. That is what is there. This is actually in the planning when we actually plan. Suppose what we actually do when the day by day actually demand is increasing, but if the way the demand is increasing, we should also add the capacity to meet up that demand. So this actually calculated that whether I will bear with that, yeah, this much of energy, I mean this much of power demand, demand shortage will be there, a demand of capacity shortage will be there, or we should install a power plant to meet up that demand. So commonly planning target is that this should be lowly 0.1 days per hour, 1 day in 10 years. This scenario should be 1 day in 10 hours. During planning, this should be taken into consideration. And loss of load probability, it measures the probability likelihood that the available generation will be less than the demand at a particular instant over a defined time period. And expected energy not served. That is, you may have, energy, expected energy not supplied to customer due to insufficient generation. Now you have the capacity, but you are not able. You have the capacity, but you are not able to serve the energy. That is value of loss load. So this is vol actually represent the economic cost of unserved electricity. Suppose if you have a loss load, suppose if you have because you are not able to serve a load to a domestic consumer, so that time domestic consumer is not much suffer. But if you are not able to serve industrial consumer, so they may suffer a loss. So high vol means the power interruption are very costly to consumer. A low vol indicates that the consumer can tolerate the short outage. If a factory losses 50,000 worth of production during an outage where 10 megawatt hour of energy was unserved, so that is 5,000 per megawatt hour. So if we are not able to serve 10 megawatt hour, and because of that the consumer lost 50,000, so that means consumer has a loss around 5,000 per megawatt hour. A force outage rate, that is actually sometimes what happen due to some there we actually predict a probability based on the statistics that suppose if you have in a power plant, suppose you have the 10 generating unit, and out of this 10 generating unit on an average in a year only one, actually you can say one generator you will not get when it is required. Due to some fault or due to some maintenance, you will not get. So if you don't get one in a year, that means there is a probability, force outage rate of probability around 10%. So this is simply whether you have the actually you have 10 generating unit, but when it is required, you are not getting due to some certain due to some fault, due to some maintenance. So that actually being assessed with this 4 outage rate. This is the levelized cost of energy because in case of renewable energy on other, which one is actually economical, that is assessed with this levelized cost of energy. If you talked about the levelized cost of energy, so you can say here we can see that is onshore wind. Onshore wind is the you can say actually more actually economical, you can say here, or it is actually easy for the consumer. You will get around 3.02 rupees per kWh, and then solar, then you can say thermal, then hydro. Now, if we talked about the first leak in the bucket in the distribution losses, so why actually we are talking about the modernization of the distribution grid again and again? The thing is that suppose there is a loss. I mean, whenever you are supplying power, there is a line loss is there because there is ohmic loss is there. Some other loss is also there. So distribution loss in India ranges from 10% to 30% or depending on the state infrastructure. So gross demand and discom substation net energy sold to the consumer divided by 1 minus distribution loss factor. So for example, a discom supplies 100 megawatt hour units to its consumer net energy. Its average distribution loss around 15%. So gross demand, that is distribution required 1176 megawatt hour. That means consumer, all the consumer is getting 100. If the all consumer wants 100 megawatt hour, but the discom required 1176 megawatt hour to supply this 100 megawatt hour because rest of the unit will be lost. So that means the extra 170 is lost at heat in the line. Second, that is intrastate transmission losses. So this state transmission utility collects the gross demand from the all discom. Now the STU must transport this power from state level injection point like state generating plant. So if intrastate transmission losses are typically lower around 3 to 5%. So if you take into assume that total gross demand from all discom is 100 megawatt hour, intrastate transmission 4%. So that time this state transmission utility should buy 10,417 megawatt hour of energy to supply 100 megawatt of energy to the discom distribution company. Interstate transmission losses are relatively low, 2 to 3%. So the central transmission utility plans the national grid. When the power is sent from the generating station in one state to discom in another faraway state, significant losses occurs on the high voltage interstate line. The total generation required from a power plant is the sum of the net energy consumed by the end user and all the losses along the entire plant. So if you see here, so discom forecasts the net demand at the distribution level. Discom adds the distribution losses to calculate gross demand. STU, state transmission utility, aggregates state gross demand and adds interstate transmission losses. CTU plans interstate transmission system considering interstate transmission losses, and generator output must cover all losses plus net demand. So if you see here, is it visible? So end user consumption around 1000 megawatt hour. So DISCOM should buy 1176 megawatt hour. In the state boundary, it will be 1225 megawatt hour. In the national boundary, it will be 1256 megawatt hour. So in the from power plant, we should get 1256 megawatt hour. Now to generate this 1256 megawatt hour, this much of energy should generate in the power plant, so that the end consumer will get 1000 megawatt of hour energy. So this is the Now, I'm just moving forward. This actually we have a limited time. So total transfer capability. The theoretical maximum amount of electric power that can be transferred over the interconnecting transmission path in a reliable manner while meeting all pre and post contingency system conditions. What is the total transfer capability? Is not a single number, but is determined by the most limiting constant among thermal limits, voltage limits, stability limits. So suppose if a transmission line is there, so it will be the minimum of thermal limits or voltage limits or stability limits. Suppose by if you take the example, total transfer capability, the minimum of thermal limit, voltage limit, and stability limit. A critical corridor between suppose region north with surplus coal power and region south with high demand is studied, and simulation show thermal limit 6500 megawatt, voltage limit 5800 megawatt, and stability limit n-1 contingency 5000 megawatt. So that time we will take the minimum of these three. So that means that total transmission capability of that line will be considered as 5000 megawatt hour. Now transmission reliability margin. The portion of transmission capacity reserved as a safety buffer to handle unexpected variation and ensure grid security. Need for TRM modeling inaccuracies in total transfer calculation. Changes in generation or load from forecast. Unscheduled or loop flows. Power takes unintended path. Please mute your mic, please.
Sir, your slide is not visible now.
Anyone?
It's not visible now. It's not visible.
Not visible.
No, sir.
It's not
Someone
visible.
else is presenting now.
Sir, someone has presenting.
Sir, it's showing
Okay.
only T.
So who are actually presenting, please stop sharing your screen.
Dr. Tataru Donepudu.
Tataru Tone Pudu. Are you there? Sir, please actually stop sharing your screen. Okay, sir. Thank you, sir.
Now it is visible.
Okay, thank you. Is it visible now?
Yes, sir.
It's visible.
Yes, sir, visible.
Transmission reliability margin, where we are there, actually measurement errors in real-time data. Purpose of this TRM, ensure actual power flow stays within safe limits, maintaining safety, stability, reliability under certain conditions. The total transfer capability, why TRM is needed already: load forecasting error, generation pattern changes, parallel path flows, uncertainties, modeling inaccuracies. TRM provides safety buffer, safe grid operation even with uncertainties. there are some methods are there to calculate the TRM, percentage method, statistical method, deterministic method, or worst case method. I'm not going into that. And TRM, next we will talk about the capacity benefit margin, CBM. Portion of transfer capability reserved by the DISCOM to access power from interconnected system for generation reliability. What will happen that actually in the transmission corridor, suppose I am using a transmission corridor, being a utility, suppose I have the transmission corridor have the capacity of around, suppose say 100 megawatt, or suppose say 1000 megawatt of power, the transmission corridor can actually supply 1000 megawatt of power. Now, being a for a utility or for a DISCOM distribution company booked that I will use your line to import a power. Suppose he has intended to import a power around 600 megawatt. Now the line has the capacity to supply power of 1000 megawatt. Out of 1000, being being a DISCOM, I will take 600 megawatt from you. It is being booked. Now I needed 600. That is already actually you can say it's a now if I intend being a utility, what I will do? So I need 600, but I will take some margin. Suppose I need only 600, but I will also keep 100 extra. Suppose 700. This 100 extra, that is actually capacity benefit margin. The portion of transfer capability reserved by the DISCOM to access power from interconnected system for generation reliability. Emergency import capacity. Why it's needed? Ensure resources adequacy during emergencies, guarantees import access even if major units fail, calculated using loss of largest unit or similar reliability criteria. How much we will keep this actually capacity benefit margin, that is calculated, then it is being decided. It's not being actually arbitrarily I will keep 100 or arbitrarily I will keep 200. This is not like that. Available transfer capability. Now, ATC is the measure of the remaining transfer capability within the transmission system that is available for commercial energy transmission after accounting for existing transmission commitment, ETC, transmission reliability margin, TRM, capacity benefit margin, CBM. Now, ATC will be total transfer capability of the line minus ETC, existing transmission commitments, TRM, transmission reliability margin, and CBM, capacity benefit margin. So, if you take an example, suppose TTC, suppose we have a transmission line that is capable of transfer of power 100 megawatt from a point, from a location to another location. Now, we have said TRM. TRM we have to here say, that is TRM we have set suppose 3% of that. 3%. So 3% of that how much? 240 megawatt. And existing commitment, suppose one DISCOM already booked. Already one DISCOM has already booked 550 megawatt, and additionally he kept an CBM, capacity benefit margin, 900 megawatt. So what will ATC, the remaining ATC will be? So this much finally TTC was 800, so subtract TRM, transmission reliability margin 240 megawatt. So that will be 7760 megawatt remaining. Subtract existing commitments, that is 550 megawatt. Then subtract capacity benefit margin 900. So finally 1360 megawatt will remaining. So why I am talking about this? Now, if you see here, suppose when a solar drops from 100 megawatt to 300 megawatt in 15 minutes. Now, okay. So ATC adequacy system in transmission planning. So generation adequacy assessment identified future needs. Now, suppose I need an import of 500 megawatt. Suppose I need, is it visible, my screen? So 1500 megawatt power I need to import from a power plant or somewhere else. So transmission adequacy assessment, check ATC versus requirement. So my requirement is 1500 megawatt. I have to import through a transmission line. Now, is ATC greater than equal to requirement? If no, then resource is inadequate planning trigger. So if you suppose you immediately need 1500 megawatt of power through a transmission line, but the transmission but the available transmission capability is less than that. So that time resource is triggering planning that your transmission is not capable to transfer this much of power currently. So if yes, then resource is adequate, proceed with the scheduling. So then you can import this power. If the ATC is greater than equal to requirement, then you can actually take that power through the transmission line. But if no, then you can't take that power. Even so, what will happen? So if suppose a state needs 200 megawatt of import, check ATC on corridor. So ATC equal to 1800 megawatt. So you are getting 1800 megawatt of power. You can the transmission corridor you will able to take power on the transmission line 1800 megawatt. ATC is there 10. So there is ATC insufficient by 200 megawatt. Identify constant line 12 at thermal limit. So the line 1, that is the line, if you name it line 12, so that is at thermal limit. So execute solution. What we can do, the conductor line 12. What we can do that we can augment the conductor of that line to so that the capacity of that capacity of the transmission line enhance. We can build a one line 1 to 3 or add series compensation. So if we can assess these three and which will be economical, we will go with that. Cost benefit analysis and technical studies, select optimal solution. Execute project, increase TTC from 200 megawatt to suppose 2400 megawatt. Now new ATC equal to initial ATC plus 400 minus 200, 2600 megawatt. So distribution grid modernization strategic workflow. So initial assessment and strategic planning. Identify the current challenges such as high losses, reliability issues, poor viability. Forecast future demand, future needs, include electric vehicles, distributed energy resources, rooftop solar and storage. Develop a clear long-term vision aligned with renewable targets, reliability standard and consumer expectation. Technology infrastructure upgrading planning. Once the vision is clear, the next step is translating into practical roadmap. Preparing a smart grid roadmap, developing an investment plan, reviewing policy and regulatory readiness. Technology then phase implement and deployment, smart meter rollout. Smart meter rollout for visibility and consumer engagement, grid automation such as for faster fault isolation, ADMS or SCADA upgrade for real-time monitoring and control, and operational optimization and performance monitoring, data analysis for operational insights, demand resource program for flexibility, cyber security implementation to protect digital asset, continuous tracking of performance, matrices like SID, SIFI and losses, continuous improvement and future proofing. Future proofing, that is actually here it has been T by mistakes. So adopt new technologies, respond to policy evaluation, enhance resilience against climate events and cyber threats. So grid modernization is the journey of continuous evolution, not one time actually upgradation. Now, key Central Electricity Authority Technical Regulation amendments. So these are the regulation. Some what actually some Central Electricity Authority Technical Standard for Construction of Electric Plant Electric Line Regulation 2002. There is a technical standard for connectivity to the grid regulation 2007, and it has been amended in 2019. So what there is some regulation is there that some criteria is there. Suppose if you add a power plant, so the SCR should be greater than equal to 5. So some criteria has been fixed up, and not only that, if you suppose nowadays if you want to add 100 megawatt of power solar power plant or wind power plant, so that time how much storage capacity you have to you also should actually install like a hybrid model. So that kind of guideline has been mentioned in these regulations. So if you have any questions, you can please go ahead. Because of the shortage of the time, I have to skip some of my slides.
Thank you, sir.
If you have any
for such an
questions, please go ahead.
insightful question.
Sorry.
Thank you,
Good
sir, for
afternoon,
such an
sir.
insightful session.
Yeah.
So now we'll move ahead with the question and answer session. So participants, please come
Good
up with your
afternoon, sir.
question.
Hello.
Yeah. Good afternoon. Good afternoon. Please go ahead.
Sir, my question is related to SciFi and SciD. What is the
Go ahead.
difference between SciFi and SciD and how they are related to each other?
SciD means system average frequency duration. One is duration. Okay, and SciFi one is that is frequency.
Okay.
If you go through if you go to the slide, or if you if you go to the SciFi and SciD, that is the average SciFi. If you talk about the SciFi, that is the abbreviation for of system average interruption frequency index. So that means how frequently power is going off for a consumer. And SciD, that is system. If you go to the full form of the SciD, that is system average duration frequency index.
Okay.
So this is the actually duration. Suppose if a consumer getting power off, so how much duration it will get off, or how much power interruption will be there. So suppose if you ask some for the utility, if you talk about the utility, you will, if you apart from this parameter, you can't compare the utility other discom to other. Suppose SciD for a discom A, it's actually suppose 5 per consumer, or per consumer per year, and for another consumer it is 1. That means the SciFi having 1, it's much more, actually you can say reliability of that discom is much better than the which have with the SciFi of 5. And simultaneously, similarly, SciD, if you talk about the SciD, so suppose that is 1 hour per consumer per year. That means one consumer will experience on an average, if we ask that for that discom, a consumer will on an average on a year, he will get a power of 1 hour.
Okay, sir.
Am I clear?
Yes, sir. Sir, I have one more question.
Yeah, go ahead, please.
Is there any software for ATC analysis?
Yeah, there is a software for ATC analysis.
What is the name of software, sir?
It's a for company to actually discom to discom it vary. For my discom, it's its own developed software.
Okay. Okay, sir. Thank you.
Okay, welcome.
Synthetic
Yes, any
inertia.
further questions? Okay.
Engineer Mondal, synthetic
Yeah,
inertia.
yeah. Listening.
Could you please elaborate a little more on this synthetic inertia and how exactly you do the thing for simulation purposes, if you have done that, or in practical purpose, practically, how do you do that? Thank you. Yes, Engineer Mondal, am I make myself clear?
Sorry.
Is it clear? The question I wanted to hear. It is not a question, rather I put it like that. The synthetic inertia for simulation purposes. How do you incorporate that, or how you do the simulations considering this?
No, actually synthetic for the, you can, if you talk about the, I haven't go through the simulation, you guys are better known about that. But the thing is that what I can elaborate what is synthetic inertia and how you can do it. I can give a small idea. That is synthetic inertia means you are adding some inertia into the system. And it may be, suppose you are having a solar power plant, along with the, you have also have a battery energy storage system. So in that case, you are, whenever you are getting any, it's a, what can I say? You can adding some inertia to the system. Though it's a battery, but you can, what we are doing, actually you are doing, you can give a support to the system for few seconds, which is required. Actually, what we have to do, because whenever you have
that exactly, I want to know what kind of support you are talking about. That this support for this much period. If we increase that amount of support, the
it
period
will
will
actually
increase a
depend.
little more.
Yeah, it will actually depend system to system. Suppose after a simulation or after a frequency analysis of the system, so we see, or worst case scenario, you can say worst case scenario, you can see that in a particular system, if you don't add the synthetic inertia, so it will around within 2 milliseconds or within 2 seconds, the system, frequency will go beyond the Nadi frequency, or it will go beyond the the
Absolutely.
minimum frequency that has been set for the under frequency relay for the generation.
Correct.
So for buying that how much you have to, if you make, how much you have to make addition, so you have to have a calculation that this much, if you add this much of calculation, that this much of frequency, this much of synthetic, if you add this much of inertia, then it will fall this much after 5 seconds or after 2 seconds. You need to, suppose more, you need more another 1 second. But ultimately, whether the frequency will settle, that is not determined by the synthetic inertia. That is determined by, that is the 1 by d plus 1 by r.
Recently, we have come across something. We were thinking like this. Just I'm sharing with you. Just please correct me. Say we are increasing the non-conventional or renewable energy sources instead of the synchronous machine-based generations. Now, one of our students is actually trying to do that. Now, after a particular percentage, what he is observing, the system is becoming unstable. Now, by incorporating some synthetic sort of inertia, right? Say inertia, we are trying to make the system a little more time stable. Okay. Now here I actually, we have suggested the student to try to see some of the literatures, whether it is possible to increase the period by incorporating this in a synthetic kind of inertia. Now exactly, I wanted to hear that what is that kind of inertia that we can incorporate for a little more time. Maybe after that period we will be able to take it back.
Yeah.
What is that you are suggesting? That yes, this can be the synthetic inertia, or
No,
what
but
you call it as
what you have to know, that is one thing is that all of you know that initial, actually what you know, the system becoming unstable, that is frequent in terms of frequency you are talking about, I think, right?
yeah, frequency angle, correct? Yeah.
Frequency stability, you are not getting the frequency stability. You are not talking about the voltage stability here. So
Yes,
frequency
not
stability you are not getting. That means now if you have also battery, so that time also that required a minimum time to actually boost the to switch on the battery, though it's automated then also in the system. But if
the
it's, you are
battery
not getting,
is one of the solution.
no, you can also flywheel type of solution you can get.
Flywheel. Okay, flywheel. Yeah, these are the terms I wanted to hear.
Yeah.
Okay, thank you. Please answer.
Hello. Yes, any further questions?
No questions, ma'am. Thank you so much. Very informative session.
Yes, other participants, if you have any question, please proceed quickly. Otherwise, we'll close this session. Okay, so now since we don't have any questions further. So we'll proceed for one screenshot. So I want to request everyone to please switch on your camera. And sir, if you can like close this.
Stop share.
Okay, okay, okay. Okay,
Yeah.
okay. Thank you, thank you.
Thank you, sir.
Thank you, everyone.
Okay, thank you once again, sir, for giving your valuable time.
Thank you, ma'am.
Thank you so much.
Ma'am, please share the feedback link.
Sure, sir. We'll share that on the chat box shortly.